All right, so we're on to another practice problem, a new transfer function here. Again, I'm going to write it in terms of s. So let's go h of s is equal to 5s plus 2 over s times s plus 10. And then, of course, we can get it into standard form. We can pull a 2 out, so we get 2 times 5 times 1 plus s over 2 divided by 10 times s times 1 plus s over 10. And the 10 up here and the 10 down here cancel, so we really just get a constant value of 1. And I can write that h of s is equal to 1 times 1 over s times 1 over 1 plus s over 10 times 1 plus s over 2. And those are my 4 factors. That's my transfer function written out by its factors. And so we can recognize these terms. Again, this is a constant k, which is just 1. This is an origin pole, okay? This is a pole at s equals minus 10. And this is a 0 at s equals minus 2. Okay, so that's our transfer function right there, broken up into its factors. So let me go ahead and plot this now. Let's plot the magnitude. I'll move this over here. Let me shrink it a little bit too so we have some room. Okay, and so let's just create our plot here. Let's just go create this. I guess we have a ton of room. I can move this over here. I can put this here. And let's just go 20 dB, 40 dB. And then we'll go minus 20 dB, minus 40 dB. This is obviously 0 dB, omega axis here. And let's go 0.1, 1, 10, 100, 1,000. And we'll put the 2 values in there as well. Let's just go 0.2, 2, 20, 200, 2,000. And this is going to be my magnitude plot of h of s in dBs. All right, so let's go ahead and do this. The first term is a constant k, right? So we know that a constant k has a magnitude of 20 times the log of k. We know that the log of 1, right, is 0. So the 20 times the log of k equals 1 is basically just 0. So that's just a flat line at 0 dB, which again, similarly to the previous example where we had 0 degrees phase, and it really does nothing to contribute to the overall response. I'm plotting it here, but just note that it doesn't really do anything for us. This is just a value of 0 dB from k equals 1, right? So that does nothing to our response. It's not going to add anything, and so we can almost ignore it, but I'm drawing it just for completeness like I normally do. An origin pole, what do we know about an origin pole? Well, we know it crosses 0 at omega equals 1, and we know that it's 20 dB per decade dropping before and after that. So let's go ahead and sketch that. So this is my origin pole. Try to do my best there. Again, that's origin pole. And then what do we have next? We have a pole at s equals minus 10. We know that a pole at s equals minus 10 means that we're going to have 0 up until a value of omega equals 10. And then we're going to get 20 dB per decade roll off at all the higher frequencies. So that right there is my pole at s equals minus 10. And then the last one I have here is a 0 at s equals minus 2, which starts at 0 dB. And then it starts rising at 20 dB per decade, starting at the value of the 0, which is s equals 2, or sorry, omega equals 2. And so this right here is my 0 at s equals minus 2. Okay, so that's everything for the magnitude that we need to sketch it. So let's go ahead and sketch it. So if we look at the first interval here, it's going to basically be from the origin out to 1. Nothing's changing. I've got this constant, or actually it's going to go all the way out to 2 before anything changes. This dropping term plus a bunch of zeros is going to just be this term that's dominating the response. So let's go ahead and just trace that right until a value of 2. And what happens at 2? Well, at 2, my origin pole and this 0 at 2 cancel each other. And so my net effect is a flat slope. So I'm going to get this flat slope up until 10, where another pole starts contributing to the response. And so then I've got pole 0 cancellation here, but then this other pole is going to pull the response down at 20 dB per decade. And so I'm basically just going to trace a parallel line there, and that is going to be the end of my response, right? So that red line right there is my magnitude response for this transfer function, okay? So hopefully the process is starting to become clear. Hopefully it's clear what I'm doing here when I sketch the 4 individual terms in the magnitude plot, and then I add them together, and I kind of just look at each interval where things aren't changing. And when I say things aren't changing, I know this is obviously changing. It's dropping at 20 dB per decade, but this term is fixed at the slope that it has, and so are all the other terms in terms of slope. Once the slope of one of these terms changes, we have to reassess. Once the slope of this term changes, we have to reassess, because now the overall response is going to change as a result of the change of one of these terms, going from one slope, which was originally 0 and no contribution, to now contributing to the overall slope of this red curve, which is the overall response, okay? So I'm going to go ahead and end this video. In the next video, we'll do the phase, and then we'll be done with the Bode plots section, and I will take a little bit of time to cover filters, which is basically just a name for what we've been doing this entire time. It's an application for what we've been doing. It's not going to be a whole lot of new material, but I think it's very important to get to that point, because that is the reason why we do all this, is to develop filters for different circuits applications. But I'm going to go ahead and end this video. I'll do the phase in the next one, and then we will be done with Bode plots. All right.